Okay, take a look around you for a second. The key in your pocket, the metal legs on your chair, they all likely started out as simple, boring blocks of metal. So, how do you get from a rough chunk of steel to the really precise, complex parts that build our modern world? Well, in this explainer, we're going to dive into the fundamental machines that make basically, well, everything. It's a question that really gets to the heart of how we make things. And the answer isn't some kind of magic. It's a powerful core idea that holds up this entire process.
And that core idea is called material removal. You can think of it like a sculptor with a block of marble. You start with way more than you need, and you just meticulously chip away everything that isn't your final masterpiece. All the machines we're about to see are absolute masters of this one single concept. They just happen to do it to metal, which in the biz we call the workpiece.
So, where do we start our journey? We've got to begin with the oldest, and maybe the most fundamental machine tool of them all, the lathe. Honestly, in so many ways, it's the bedrock of modern machining. Now, here's the key concept, the thing that makes a lathe so powerful. Unlike, say, a drill where the tool is the thing that's spinning, on a lathe, the workpiece itself is what's rotating at a really high speed. Meanwhile, a stationary tool is brought in to do the actual cutting. This one simple idea, it's the secret to everything a lathe can do. Let's just break that down real quick. First, you clamp your block of metal in there and get it spinning, and I mean fast. Then, you carefully bring a super hard cutting tool right into it. That tool then just peels away ribbons of metal, creating a perfectly round cylindrical shape. If you've ever seen a potter's wheel shaping clay, it's the exact same idea, just for metal and with just incredible precision. And as you can see here, the lathe is unbelievably versatile. It's not just for making simple round bars. By moving that cutting tool in different ways, you can create perfectly flat faces on the end of a part, drill precise holes right down the center, cut the threads for a bolt, or even create one of those cool, grippy, textured patterns. That's called knurling. Okay, so the lathe is the undisputed champion of anything round. But, our world is full of things that aren't round. So how do you machine a perfectly flat surface, like on an engine block? A spinning workpiece just can't do that. For that job, we need a totally different way of thinking. And this brings us to two really interesting machines, the shaper and the planer. They both do the same thing, create flat surfaces, but they work in opposite ways. On a shaper, the workpiece sits still while the cutting tool moves back and forth over the top. But on a planer, which is built for absolutely massive jobs, the tool is stationary and the entire heavy workpiece slides back and forth underneath it. So the takeaway is pretty simple. It all comes down to what's easier to move, the little tool or the giant hunk of metal. And get this. This is a piece of absolutely brilliant, time-saving engineering. A shaper only cuts in one direction, on the forward stroke. The whole trip back is just wasted time, right? And time is money. So some clever engineers in the 19th century developed the quick return mechanism. It's this amazing system of gears and levers that makes the tool move slowly and powerfully on the cutting stroke, and then, zip, it flies back incredibly fast on the return. It is pure mechanical genius, all just to be more efficient. All right, let's switch gears to our next big idea. So far, we've spun the workpiece to make round parts, and we've moved either the work or the tool back and forth to make flat parts. But what happens if we flip the whole script and we focus on spinning the tool instead? Well, that simple change unlocks a whole new universe of shapes. The most basic example of this, of course, is drilling. We've all used a drill. A rotating cutter, the drill bit, gets pushed into a stationary workpiece, and boom, you got a hole. It's really the purest form of that rotating tool principle. But a simple drilled hole is often just the beginning. From that starting point, as you can see here, a whole bunch of other rotating tools can come in and perfect it. You can bore the hole to make it a little bit bigger, you can ream it for a super smooth and precise finish, tap it to cut threads on the inside for a screw, or even countersink the top so a screw head can sit perfectly flush. Okay, so if drilling is the simple intro to rotating tools, then the milling machine is the main event. The source material for this calls it the most versatile of all machine tools, and for a very, very good reason. It takes that idea of a spinning cutter and gives it the freedom to move in pretty much any direction, up, down, left, right, in, and out, to create almost any shape you can dream up. And the level of detail you can get into is just incredible.
I mean, this table shows how even the direction the cutter spins compared to how you're moving the workpiece makes a huge difference. You can think of it like this. Up milling is like trying to push a lawnmower through really tall grass. The blades are fighting your direction of travel. But down milling or climb milling is like walking with the mower as it cuts. The blades are moving in the same direction you are, pushing down and giving you a much cleaner cut. It's a subtle thing, but it has a massive impact on the finish of the part.
So at this point, our machines have cut apart into its basic shape. But in the world of high-precision engineering, we're talking medical implants, aerospace parts, close enough is never good enough. The surface might still have these tiny, microscopic tool marks. To get a truly perfect part, we need to go through a final set of finishing processes.
This is really the path from rough to totally refined. First, grinding uses a wheel that's basically like a super precise spinning piece of sandpaper to take off tiny amounts of material and hit incredible accuracies. For an even more perfect, almost mirror-like surface, lapping uses this fine, abrasive paste. And for the inside of cylinders, like in your car's engine, honing uses these special abrasive stones to create the perfect surface texture so the piston rings can seal just right. It's all about maximizing power and efficiency.
So after all that, what's the big takeaway here? Well, it really all boils down to two fundamental ideas that pretty much built our world. You can either rotate the workpiece and bring a stationary tool to it, like on a lathe, or you can keep the workpiece still and rotate the tool, like on a drill or a milling machine. Almost every single precision metal part that exists is a product of one of those two big ideas. And their impact, it's almost impossible to overstate. To put a number on it, you could say that the vast majority, we're talking well over 95%, of all the precision metal components that make our modern lives work, from the tiniest screw in your phone to a massive gear in a wind turbine, have been shaped by one of these core machine tools. These machines, operated for decades by the skilled hands and sharp eyes of machinists, they were the engines of the Industrial Revolution, true masterpieces of mechanical engineering. And that leaves us with a really fascinating final thought. What happens when you take these brilliant physical principles of material removal and you connect them to the digital brain of a computer? Well, that, of course, is the story of CNC machining, and that's a topic for another day.